Good day, students. Probability, some more. Video 11, part E. Couple of examples. The examples are going to get trickier, so pay attention. Example 1. It's known that approximately 45% of all people have type O blood. 40% have type A blood, 11% have type B blood, 4% have type AB. Forget the positive and negative for now, well, for the whole example, and no one can have more than one type of blood. That last sentence here tells me disjoint. You cannot be type A and at the same time type B, or at the same time type AB. These are 4 disjoint events in this probability experiment. Draw and label the Venn diagram. Always put the big rectangle. This is sort of the universe, the whole sample space, and I like to label it up here at the top. Oh, this is just all people. Okay, that'd be 100% of the probability. Now, I'm not going to draw the circles this time. I'm going to sort of just carve this up. Let's see, 45% are type O. Let me just put a line here. This is about 45% of the area of this rectangle. So I can label that here, 45%. This is type O. 40% are type A, so another little, maybe about this much here. Here's your 40% type A blood. That last piece is 15% total. It's 11% for type B, so maybe we'll do like this. Here's 11% for type B, and the bottom little piece here, 4% for type AB. Don't confuse this with a uniform distribution just because I made a rectangle. This is just a Venn diagram. If you want to use circles, it's fine. It's just the circles wouldn't overlap because the events are disjoint. And you probably would draw this with 3 circles and then the outside space that's sort of inside the rectangle but not in the circles would be one of the types of blood. So I think this is a clearer picture rather than the one that we've seen before about Canada and Mexico. All right, so there's that. It's part B then. If we randomly select one person at the blood drive, give the probability that they are type A or type AB. All right, I'm going to keep the picture because I'm lazy, but you can see in your notes we're doing type A or type AB. We'll put the answer over here on the side. Probability that you're type A or AB. Blood types are disjoints. I can use the addition rule for disjoint events. This is just probability of A plus probability of AB. Add them up, 40%. Plus AB is 4%. No calculators, 44% is the answer. I could have converted to decimals. When you're adding and subtracting, it's okay to keep them as percentages, but one word of advice, when you start multiplying things, definitely go to decimals. Okay, so a simple application of the addition rule here. Part C, we'll flip the slide, see if we can squeeze this in. Let's see here. Part C, can I squeeze it without erasing? Give the probability that a random adult is not type O. Okay, you can visualize it, use the Venn diagram. 45% of adults are type O. So using complement rule, the rest are not type O. It's 55%. Take the whole rectangle, we've used up 45%. So all of this to the right of the line here is not type O. I'll throw the answer here. It's 55%. Pretty easy to sort of do without invoking any of the formulas, but I'll squeeze it here to the left. Probability that you are not type O is exactly 1 minus the probability that you are type O. I'm going to abbreviate that with, that's O blood, not the number 0. 1 minus the probability that you're type O. So this is 1 minus, I guess this is as a decimal, so minus the 0.45. 1 minus 0.45 is 0.55, that's the 55%. pretty easy one. Probably I would just take the answer because it's obvious for most of us. All right, I guess I will erase this for part D here. Same example, 2 more questions. All right, next page, part D. Presuming the next 2 people that walk through the door are unrelated, you know, that tells me independent, right? We have to make sure when we're doing these calculations, if the next 2 people, as long as they're not brothers or sisters or something like that, then I got to presume that their blood types do not influence each other, be independent. What's the probability that they are both type A? All right, hardest thing for students is sort of putting the words into the formulas. I have 2 people, I'm going to use the independent rule, and what's the probability that they're both type A? Here we go. Probability that they're both A is exactly the same as the probability that the first person is type A and second person is type A. So we have to sort of translate words into ands and ors and formulas, right? Both type A, first is a type A and the second is type A. When I see that word and means multiply. I have the independent rule. This is exactly the probability that the first is type A times the probability that the second is type A. I know this from, we're told at the beginning of the problem, the chances that any randomly selected person is type A is 40%. So this will be equal to, got to do decimals here for multiplying, 0.40 times 0.40. It looks like 0.16. I'm just going to sort of peek there. All right, good for me. 0.16. And we should be good at this by now, but that's 16%, right? So 2 randomly selected people, 16% chance both of them, the next 2 people, are both type A. And we use the multiplication rule for independent events. Okay. Party. They're getting trickier, so let's focus. Make some space here, might go off to the sideboard. What do we have? Party, students. Suppose we desperately need some type A blood. There's an emergency. What's the probability that for the next 2 donors, at least one of them is type A? What's the probability that for the next 2 donors, at least one of them is type A? Okay, so let's think about this. Maybe be able to squeeze it up here. So I want to sort of enumerate what possibly could happen with the 2 folks coming through the door. So here's the next 2 people. All right, and I guess the best case scenario, at least for this, we desperately need A, is that I get A and A, right? So that'd be the best thing because we're desperate here. Another thing could happen would be, I guess, that the first person was an A, and then the second person is anything else besides A. So it's probably clearest. I'll just put not A. I could put A complements. I could list out B, A, B's, O. Okay, so that's 1 and 2. First person could be not A. And the second person could be A. All right, and then the worst case scenario for our emergency here is, get the double whammy here, is a not A, and I get not A. Okay, so with 2 possibilities for each person and 2 people, sort of like 2 times 2, there's 4 outcomes here. I'm looking for at least one of them is type A. Is at least one of them type A? You betcha, right? So there's a check mark for that one. How about for the second one? Is at least one of them type A? Absolutely. Is at least one of them type A? Yes. Down at the bottom, That's the one bad one, right? That's the only case scenario where we don't get any A. What I'd like to do now is determine the probability of each of these 4 rows happening. Okay, so all we're going to do is sort of apply the multiplication rule for each row. I have 2 events. They're independent because this person doesn't affect this person. So maybe we'll put a column here for probability. And in each of these 4 different outcomes, I can use the multiplication rule. Okay, so let's look at the top one. There's a 40% chance that this person's A. There's a 40% chance that this person's A. This is like probability of A and A, but I won't write that. I'll just say the probability of that happening is 0.4 times 0.4. That's a 16% chance that the top row happens. Next row down. First person's A, second person's not A. So what's the chance that anybody is A? It's a 0.4. Now we start combining rules. It does get a little tricky, but if there's a 40% chance that somebody's type A, what's the chance they're not type A? Well, complement rule, right? It's 60%. So the not A, that's a 60% chance for the second person. And so for that exact outcome to happen, first person's A, second person is not A, is a 0.4 times a 0.6. I am just going to put 0.24 and presume I can multiply in my head. All right. Go down to the third row. Not A. We know that the chance anybody is not A is 60%, 0.6. Second person now is the A. A is 0.4. Probabilities, independent events, I can multiply. I know what this one is, I hope. It's the same as the previous one, right? 0.24. And last but not least, the worst case scenario, because we're desperate for A. 2 people, no A. 0.6 probability for the first, independent of the second person, so I multiply 0.6 times 0.6 equals 0.36. These are the 4 outcomes. In fact, this is sort of the sample space, those 4 events over to the left. So if I did this correctly, this should add up to 100% or 1, and this is 40 and this is 60. So if you added up these probabilities, you would get exactly what we need, 1.00. Okay. Now, unfortunately, we haven't answered the question yet, but hopefully we have gained some insight to this problem. Okay. Back to the question. What's the probability that for the next 2 donors, at least one of them is type A? The straightforward way of doing this is saying, all right, the 3 check marks, I just add them up. Okay? So if I added up those 3 numbers, probability at least one of them is type A, 0.16 plus, 0.24 plus, 0.24. If I add that up in my head, what are we going to get? About a 0.64, I think. And so that's the answer to the question. Okay, there's a lot of work involved. We really had to think what was happening here. Invoke a couple of rules. In fact, pretty much every rule that we've learned, we've invoked in this problem. Double checking my notes here, make sure I got the same answer. All right, good. 64% chance. There's one last. Seems like a lot of work to do it this way. And what if I had, say, I don't know, 5 people coming through the door? What's the chance we get at least some type A blood with 5 people? So we'll go over here, do this one last way, and then we're going to move on to that second example. Maybe we can use the complement rule way to answer this question. Okay, and all it is, it's using the same ideas that we developed on the main board there. Okay, so let's write this out. Probability that I get at least some type A blood. Some type A blood was both people or A, or the first or the second person was type A. I can use the complement rule, and one rule of thumb, if you ever see an at least type problem, you can invoke the complement rule in almost every case. But just think about it, make sure that you understand. 1 minus, what's the opposite of at least somebody having some type A blood? The complement of that, or the opposite, is that nobody has type A. Out of my 2 people, I go 0 for 2. Right? This is 1 minus the complement. The complement is that either person is type A. Read this a few times after the video. Make sure that you see this complement events. All right. Now we already calculated this. It's in your notes. We did the first person's not A, second person's not A. Neither person type A, first person not A. Remember, this was 0.6 for being not A for the first person. This is 0.6 for being not type A for the second person. It's the bottom row of the chart on the main board. It's in your notes. Row 4. 1 minus this, we'll get the same exact answer. It's 0.64. I wanted to go through the enumeration part just to show you the possibilities, but in most cases, when we do these at least problems, we'll tackle it the complement way. Okay? And so if you don't get it this time, don't be scared, because we'll do plenty of examples. All right? In fact, the next example that we'll start right now. All right, back to the main board. I guess in the year 2024, when we redo the notes again, we'll make this into a new video, but feels like you're getting along one, students. I guess the time, but I don't want to use up my carnival tricks like I did that one video. Part A, next page. Your instructor is going to create random groups of 4 students. At Cecil College, it's known that 85% of statistics students have never taken any calculus. 10% of STAT students have taken Calc 1, and 5% of STAT students have taken Calc 1 and Calc 2, or at least 2 calculus courses. Okay? Those are disjoint up top. Either you've had no calculus, exactly 1 or 2 or more calculus classes. We'll put you into groups of 4 at random. Random groups. Hints at independence. Give the probability that no one in your group of 4 has ever studied any calculus. Here it comes. Probability. No one has any calc is exactly the same thing as the probability. Let's think. I have 4 students. First person, no calc. Second person, no calc. Third, fourth, same deal. So, first person, no calc. And, has to be and. Second person, no calc. And, third and fourth. Can I do this? Lazy, I ran out of board, but right. First, second, third, and fourth, no calc. We know that 85% of Cecil Math 127 students have never had calc. Because you were put into your groups at random, and I'm doing an and, all I do is multiply. This will be, oh, I got it. This is probability first person had no calc. Times second person had no calc. Times probability third, times probability fourth. Here, there's a lazy man's way of notating that. Here's for the first person, 0.85. Times, here's for the second person, 0.85. Here's for the third. Here's for the fourth. I love it if you write it 0.85 to the 4th power. I don't have any room to do this, but let me just put the answer here in the box. 0.85 to the 4th is 0.522. It's a little bit better than 50-50 odds that nobody in your group has ever had any calculus. All right. So that's A. B and C we'll call it a day. Part B, let's see what we've got here. All four members, what's the probability that all four members of the group have had some calculus? First person has had some calculus, and the second person has had some calculus, and the third and the fourth. By the way, make sure you're answering the question, what's the probability that you've had calc? We do have to add the 10% people for Calc 1 and the 5% people for Calc 2 or more. So probability that you've had calc is 0.10 plus 0.05 is a 0.15, right? 85% have not had calc, must be 15% have had it. Those are complements. All four members of the group have had some calc. Probability all four have had calc equals, we're going to be invoking the multiplication rule for independent events. Remember, the instructor put you into groups randomly. I have a feeling if we let people choose their own groups, the calc people might sort of end up together, wouldn't be independent, but this is independent. So what I'm going to do is I'm going to take that 0.15, that's for the first person. I'm going to multiply it for the probability for the second person has had calc. Here's for the third. Here's for the fourth. I skipped about 3 lines of writing the words out, but we've seen a few examples at this point. This is 0.15. It's raised up to the 4th power because I have 4 students. Think to yourself, what if I had groups of 5? What would change in this problem, right? We can make those changes. But here's groups of 4. 0.15 raised up to the 4th power is 0.0005. Very small chance, small odds of that. But think about that. It's pretty rare for somebody to have calc at Cecil College, just 15 out of 100. And I have to do it again and again and again. As a percentage, this is 0.05%. And if you looked at the odds, this is quite rare, right? This is 5 out of 10, 100, 1,000, 10,000? It's a 5 in 10,000 chance. 5 in 10,000 chance. If I reduce that, this is, give or take, this is about 1 in 2,000 chance. That if I randomly created groups, we'd get the super calc group where all 4 students had some calculus. Right? 1 in 2,000, pretty rare. All right, letter C, then we're done, I think. Yes. In your group of 4, give the probability that at least one person in the group has studied some calc. Complement rule, for sure. We won't take the time to enumerate like we did for the previous example. Blood types, 2 people walking through the door. But the event that we're interested in is at least one person out of 4 that has had some calculus. Could be the first person alone. Could be persons 3 and 4. Could be 1, 2, and 3. Could be that calc supergroup. There are so many things that go into what I've circled there. At least one person in the group has had some calculus. So what I'd like to use is the complement rule. Probability at least. I guess I can write it this way. Probability at least someone had some calc. Right, your group of 4, like what's the chance at least one person has had some calculus? All those combinations. There's only one combination that's not in that, so we're going to use the complement rule. 1 minus the probability of the complement. The complement of at least someone having some calculus is that no one. had any calc. These are tricky for students, but make sure that you understand that these are the opposites or the complements. At least someone having some calc is the complement of no one ever having any calc. All right, equals. This is 1 minus something I believe we calculated already up in part A. Part A, give the probability no one in the group ever had studied any calculus. If you look up at the top, we already did that one, so I will just grab that number. Looks like a 0.522. Remember what we did, we took that probability and multiplied it by itself times 4, 4 times. And 1 minus 0.522 is 0.478, or roughly 47.8% chance. So it's approximately 50-50. And think about that. There's a 52% chance that nobody had any calculus in your group. So the rest, are about 47.8% chance that someone had some calculus, right? Those are opposites or complements. All right. We'll plug on, but we're done videotaping for today. So thanks for watching, and we'll see you again in class.